Okay, so in the last video we just introduced this idea of what's called L'Hopital's rule. Specifically, we're looking at the 0 over 0 case right now. And again, the idea is that if we have two functions that are differentiable about our point that we're trying to take the limit, so both of these things have derivatives about x equals 1, and the other thing is the denominator can't be 0 for those values around it. It's okay if it's derivative 0 at a, but it can't be 0 elsewhere. The denominator just can't be a 0. If the denominator is 0, we're out of luck. Okay, if that's the case, and both the top and bottom have a limit that goes to 0, then it turns out the limit of the fraction f of x over g of x as x approaches a is the same as the limit of the fraction involving their derivatives. And you can see immediately the benefit here, especially if we're dealing with polynomials. Well, eventually taking derivatives of polynomials, we're going to eventually get down to something that has a derivative that's a constant. And that's actually the case in this example here. Now, how would you have done this without L'Hopital's rule? Some of these limits are ones you could have done without L'Hopital's rule. So this one here, you actually would do some factoring. You could actually factor the top by grouping here, and you'll eventually be able to cancel out a factor of x minus 1, I believe is how this would work. Or you could have done long division, divide x minus 1 into that, and see what you get that way as well. But here we're just going to directly first recognize that, hey, this is a 0 over 0 limit. Right? This is a limit involving 0 over 0. So we apply L'Hopital's rule and say, since both top and bottom are going to 0, we can now apply L'Hopital's rule, take the derivative of the top, 3x squared plus 2x minus 1, and take the derivative of the bottom. And now we have a limit that no longer involves 0 over 0. So we can just evaluate it. And we compute it. 3 plus 2 is 5, minus 1 is 4. So it's 4 over 1, so this limit is approaching 4 when x is approaching 1. And we can verify that graphically. So why don't we actually take a look at that one graphically. Real quick here. Y equals x to the third plus x squared minus x minus 1 all over x minus 1. So of course, there's a hole in the graph at x equals 1. But if you look at the graph here, as we approach 1, the graph is approaching 4. Exactly what we found. Again, it's not actually exist at x equals 1. You can see if I put the graph of x equals 1 in here, right, it doesn't actually, they don't actually intersect. Right? This graph doesn't exist at 1. The green graph doesn't exist at 1. But you can see if I actually come to that point, it even says there at 1, that it's undefined. Okay. But we can see that the limit is actually approaching 4. Which kind of confirms our result that we just had.